Now comes another important application of derivatives, which is optimization. Optimization problems are extremely important in science and engineering. It's one of the important application of derivatives. Optimization is basically the act of achieving the best possible result given under some circumstances. Like in design, construction, maintenance, engineers have to take decisions. So the goal of all such decisions is either to minimize the effort or to maximize the benefit. The effort or the benefit can be usually expressed as a function of certain design variables. So it's a process of finding the conditions that give the maximum or minimum values of the function. Optimization, in its broadest sense, can be applied to solve any engineering problem like design of aircraft for minimum weight, optimal trajectories for space missions, optimal design of electric networks, shortest routes, minimum processing time in production system, optimal control, etc. So optimize is to make as perfect or effective as possible. In calculus terms, for anything optimal, we will be searching for some sort of maximum or minimum. Okay. Now comes the procedure for solving the applied maximum and minimum problems. In step one, we draw an appropriate figure and label the quantities relevant to the problem. In step two, we find a formula for the quantity to be maximized or minimized. In step three, using the conditions stated in the problem to eliminate the variables, express the quantity to be maximized or minimized as a function of one variable. In step 4, for the interval of possible values, uh, uh, find the interval of possible values for this variable from the physical restriction in the problem. And in step 5, if applicable, use the techniques uh, which were discussed in the previous lectures to obtain the maximum or minimum. Now comes the classification of optimization problems. The applied optimization problems that we will consider fall into following two categories. Category one is the problems that reduce to maximizing or minimizing a continuous function over a finite closed interval. And the second one are the problems that reduce to maximizing or minimizing a continuous function over an infinite interval or a finite interval that is not closed. So here is a small note. For problems of first type, the extreme value theorem guarantees that a problem has a solution, and solution can be obtained by examining the values of function at critical points and at endpoints. However, for problems of second type, there are relative extremum of appropriate type on the interval. Then theorem guarantees the existence of a solution and provides a method for finding it. In cases where theorem is not applicable, some ingenuity may be required to solve the problem. Now comes the first problem, which involves finite closed interval. A garden is to be laid out in a rectangular area and protected by a chicken wire fence. What is the largest possible area of the garden if only 100 running feet of chicken wire is available for fence? Now, for finding the minimum or maximum of something, the first step is to draw an appropriate figure and label the quantities relevant to the problem. Now, here is an appropriate figure of the relevant of this problem, and the quantities here are expressed, x and y. Now, this is the condition perimeter, which is given in the question that uh, you are only given with 100 running feet of chicken wire. So the perimeter of a rectangle is 2x plus 2y, it is equals to 100. Now here x denotes the length of the rectangle, y denotes the width of the rectangle, a is the area. Now second step is find a formula for the quantity to be maximized or minimized. What you have to maximize is you have to maximize, you have to find the largest possible area. So area of a rectangle is length into width. Now this is a function of two variables. Since the perimeter of a rectangle is 100 feet, the variable x and y are related by the equations 2x plus 2y equals to 100. Now this is a function of two variables. We can convert into the function of one variable by eliminating one of the variables. So taking y in terms of x, y equals to 50 minus x, substitute the value of y in equation 1, we get a is equals to x into 50 minus x. So the equation becomes 50x minus x square. Now this is our new equation, and area is a function of one variable. Now what x represents? X represents the length here, and length cannot be negative. And because the two sides of length x cannot have combined length exceeding the total perimeter of 100 feet, so the variable x must satisfy uh, these values. It should be between 0 to 50. The value of x cannot be exceeded. So thus we have reduced the problem to that of finding the value of x in the closed interval 0 to 50, for which the area is maximum. And we know that if a function is continuous on a closed interval, then a function has its minimum or maximum value either at the end points or at the critical points. End points are given here. We have to find the critical point. So what we'll do is we'll take the derivative of equation 3 and substitute it equals to 0. So we get x equals to 25. So this critical point belongs to the interval 0 to 50. So it's the critical point. Now substituting these values, different values of x in equation 3, which is basically 50x minus x square, we get different values of area. Like when x equals to 0, value of area is 0. When x equals to 25, value of area is 625. And when x equals to 50, value of area is 0. So the maximum area of 625 square feet occurs at x equals to 25. Substituting the value of x into, we get the value of y. So the rectangle of perimeter 100 feet with greatest area is the square with sides of length 25 feet. An open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal size from the four corners and bending up the sides. What size should the squares be to obtain a box with largest volume? Now you have to obtain a box with the largest volume, and you have to cut the squares from all four sides, and you don't know what should be the length of each side. Now figure A illustrates the cardboard piece with squares removed from its corners. Now x represents the length of sides of squares to be cut out, and v is the volume of resulting box. Because we are removing a square of side x from each corner, the resulting box will have dimension 16 minus 2x by 30 minus 2x, while the original dimensions of the box were 16 by 30 inches and by x. Since the volume of a box is the product of its dimensions, the volume of a box is length into width into height. So v equals to 16 minus 2x, 30 minus 2x, and taking height as x, multiplying all of them, we get this expression. Volume expression is already in terms of single variable, so there is no need to convert it into a single variable. The variable x in 1 is subject to certain constraint or restriction. Because x represents the length and length cannot be negative, and because the width of the cardboard is 18 inches, so we cannot cut out squares whose sides are more than 8 inches long. Thus the variable in 1 must satisfy this condition 0 to 8. And hence we have reduced our problem to finding the value of x in the interval 0 to 8, for which 1 is maximum. Now from 1 we'll find out the critical point. So take the derivative of equation 1 and substitute it equals to 0. We get two values of x. X is 10 by 3 and x is 12. Now check which of the value is the part of this closed interval. Yes, 10 by 3 is the part of this interval while 12 falls outside the interval, so we won't take 12. So the maximum value of the volume occurs either at the critical point 10 by 3 or at the end points, which are 0 and 8. Substituting all of these values in equation 1, we get when x is 0, the value of volume is 0. When x is 10 by 3, the value of volume is approximately 726, and when value is 8, the value of volume is 0. So the greatest possible volume is 726 cubic inches occurs when we cut out the squares whose sides have length 10 by 3 inches. Now moving towards the next example, the figure shows an offshore oil well located at a point W that is 5 kilometers from the closest point A on a straight shoreline. This is 5 kilometers away. Oil is to be piped from W to a shore point B that is 8 kilometers from A. This is 8 kilometers from A by piping it on a straight line underwater from W to some shore point B between A and B, and then on to B via pipe along the shoreline. If cost of laying pipe is 10 lakh dollars per kilometer underwater and 5 lakh dollars per kilometer over land, where should the point P be located to minimize the cost of laying the pipe? Now, this is the problem. The distance of point W from A is 5 kilometers. The distance from between A and B is 8 kilometers. Distance between A and P, if distance between A and P is x, then obviously distance between P and B will be 8 minus x. Now you have to find out uh, the point P. The location of point P to minimize the cost of the pipe. Now let's start the solution. Let x be the distance between A and P. So the distance between A and P is x, and C is the cost for entire pipeline. So from figure we see that the length of the pipe underwater is the distance between A and W. So by Pythagoras, it's the distance between W and P. So by Pythagoras theorem, the length is under the radical x square plus 5 square. So x square plus 25. This is your equation 1. Also from the figure, the length of the pipe over land is the distance between P and B, which is 8 minus x. So this is equation 2. From 1 and 2, it follows that the total cost for the pipeline is 1 million or 10 lakh multiplied by x square plus 25 plus 1 by 2 into 8 minus x. Why it's 1 by 2? Because the cost is 5 lakh dollars per kilometer over land and 10 lakh dollars per kilometer over water, underwater. That's why 1 is here and 1 by 2 is here. So multiplying them, we get this equation, equation 3. Now, as the distance between A and B is 8 kilometers, so the distance x between A and B must satisfy 0 to 8. So we have thus reduced our problem to finding the value of x in the interval 0 to 8, for which the cost is minimum. Since the cost function is a continuous function of x on the closed interval 0 to 8, so we can use the previous method to find the minimum. From equation 3, we take the derivative of cost function, substitute it equals to 0, we get two values of x, plus minus 5 by under the radical 3. As the number minus 5 by under the radical 3 is not a solution of 4, so it should be discarded, leaving x equals to 5 by under the radical 3 as the only critical points. Since this point lies in the interval 0 to 8, so the minimum must occur at one of these values. Substituting all of these values of x in the cost function, we get these results. So the least possible cost of pipeline is this, and this occurs when the point P is located at the distance of 5 pi under the radical 3, which is approximately 2.89 kilometers from point